Well, you might have noticed that most of the ones I did already in this chapter were indefinite integrals, mostly because then we don't have to do that additional step of evaluating. But there is a very important thing about additional step of evaluating when it comes to making substitutions. Because remember, as I said, that at the end, we always have to put it into x. Same thing applies. If I look at this problem, I have these limits of integration 1 to 4. Those 1 to 4, they go to x. So if I change to u, it's not 1 and 4 anymore. Okay? So I have two options. I can change the limits as well, and then I don't have to change back to x at the end. I can just shove in the new limits, or I can not change the limits and change back to x in the end. It's like the same amount of work either way. So it really doesn't matter. It's just a personal preference. So sometimes I'll do it one way, sometimes I'll do it the other way. Let me say this one looks horrible. Um, you might think it might be better to maybe do some kind of, yeah, there's not really much I could do because I can't really break up the top thing. So it kind of looks horrible, but let me try just taking the bigger square root because the bigger square root's going to be probably maybe worse, right? And making that my u. Then if I do du dx, right, this is 2 plus x to the 1/2, right? So when I take the derivative, I'm going to have 1/2 x to the negative 1/2. Okay? Or du is 1 over 2 root x dx. Well, now this looks promising, right? Because the 2 is just going to go over here to du, and then I'm going to have dx over root x, and I can substitute that guy right there. See? This dx over root x, this is my dx over root x. And let me rewrite that. 1 to 4 square root of 2 plus root x times dx over square root of x, right? So it's the same thing. So now I can easily substitute um, square root of u, and then this dx over root x is going to be 2 du, but I have my limits, so I have to change the limits. So I'm going to have to go back and figure it out. Okay? So when x equals 1, I just have to substitute that into the equation for u. The substitution that I chose for u was 2 plus square root of u. So u equals 2 plus square root of 1. So that's 3. So the 1 turns to a 3. And then now we're going to the next one. When x equals 4, u is 2 plus square root of 4. So that's 2 plus 2, so that's 4. All right, done with that. Okay, so now what? Now I just go ahead and do this. So I've made a mess of my work. I'm just going to rewrite where I was down here so we can see it a little bit better. So I've got from 3 to 4 of 2 root u du. Okay? So now I have 2 times u to the 3 halves over 3 halves, evaluated from 3 to 4. So can I clean that up a little bit? I got 4/3 u to the 3 halves, evaluated from 3 to 4. So I do not have to go back to x because I already changed the limits from x to u. So now I just go ahead and evaluate here. This is, I'll pull out the 4. So this is going to be 4 to the 3 halves minus 3 to the 3 halves. Oh, well, that's not going to look great, right? So this is just going to be some sort of irrational number because I have a 3 to the 3 halves. But 4 to the 3 halves is okay That's just 8, but this is like 3 root 3. We can just leave it like that. Okay, that's not gonna, it can be a little bit simpler, but not by much. So yeah, if you want, again, this is a sort of thing in my class, if you just leave it like that, that's fine with me. If you want to write it like this, that's fine with me too. Um, I don't really want it to be a decimal, but if you gave it to me as a decimal, I, would live with that. Right? As long as I see how you got there. So the most important thing here, okay, let me just tell you, we could also have put this back, redone it, and then just evaluate it at the 1 and 4. It would have been the same thing, same amount of work, everything. The only thing you want to do is make sure that you don't write the wrong limits for the wrong variable because then you'll just get it wrong. So, yeah. All right, let's do another one. Oh, this is a little bit different, this one. Okay, this one, I'm going to tell you, you can look at this right now and you're like, all right, what? Because if I'm looking for something that looks like a chain rule, this is not it, right? This looks like something you would not be undoing the chain rule. This looks like a product. This looks like x to the fourth times sine x. There's no sine and derivative of sine is cosine. There's no x to the fourth derivative that is 4x cubed. That's not anything here. So this is not going to be doable by u-substitution. So you can try those. I'm just going to write it here though, or u equals sine x does not work with u sub, right? Because it would be du equals cosine x or du equals 4x cubed. It's kind of a mess. We don't have that. This is, in fact, a different kind of problem. If you actually had to evaluate this integral, you need integration by parts. That's chapter 7. So what is it doing here? So this is just if you see something and don't know what's going on, but you recognize that, okay, it is a definite integral and there's some kind of symmetry here, right? Because I'm on the same side. I've got pi over 3 and I've got minus pi over 3. So we did talk about symmetry. So we know that an odd function over an even interval is going to be 0 because you have the same amount of stuff. Now, I don't know what the heck this looks like. I know it's x to the sine x, so it's going to do something like this. I don't know what, but it's going to do something like this, right? So the same amount of stuff on the right-hand side is positive and the left-hand side is negative, or vice versa. So we look at this and we don't have to actually even do it. We can immediately say, haha, this is 0. Because, but you have to say why. Just give me a 0. Because an odd function integrated over an even interval is 0 by symmetry. Okay, so we have to prove that we have an odd function, right? So f of x is equal to x to the 4 sine x is an odd function. How do we know this? Well, x to the fourth is even, sine x is odd. Functions aren't like numbers. Odd times even is odd. That's annoying. But what does it mean for something to be an odd function? F of negative x is equal to negative f of x for an odd function. And for our function here, We have put in negative x. We have this, and then we have this sine of, but sine of negative x is negative sine of x. So this is negative f of x. So that is your justification. A accurate graph of a simple function is also an acceptable justification. This, what I drew here, is a crappy graph. It's not an accurate graph. It's just giving you some vague idea. Okay. If you wanted to use a graph as a justification, to make it be a right graph, you can use a graphing device. Right. Well,